Okay, let me share my screen. Here it is. This is not relevant actually. Okay, here we are. So this is the website as usual. Let me go to our tutorials. And here, let's go to the exercise. You remember that we were talking about the application of the CERC formula, and I think this is the text of the exercise. I don't think I need to read it again, and so let's assume that you remember. I just wanted to keep it here because I may need later the picture that is placed here in the second page. So I just want to keep it here now. And let me jump back to the example of the R file. Let me open it and let me save it and open it with the text editor. Just 1 second, I need a file manager. Here I am, desktop, and here I have, just 1 second, because I didn't save it here. I think it is here, just, here it is. Okay, so let me open it. And this is the file, the R file that we were talking about last time. So let me open an R window, which looks similar to the window that you have. Let me enlarge it, and just let me change the font because it's a bit too tiny. So here we are. Sorry. Appearance, okay, here it is. Size, let's put 14. Select. Close. Okay, good. Now, let's try to make a summary of what we achieved last time. We installed this software, this new software, and we learned how to use it. We did some basic introduction, and we learned some basic instructions how to use the program, and also we discussed the pros and cons, the advantages and disadvantages of using a software that is not really user-friendly, but it is just because it's not user-friendly, it's much more powerful. Again, we discussed the basic instructions, and then we started to develop our exercise by making a cut and paste from the console or to the console from the, sorry, it's not here. 1 second. Give me 1 more second. I need to find out the, here it is. So we made a cut and paste from this file, which reports all the R instructions. We cut from here, we copied from here and pasted to the console. So let's try to repeat what we did. Let me select the first instructions up to the last but one that we inputted into the console last time. So these are the instructions which I selected. Again, from the first one, I skipped the lines of comments. From the first one to the last but one that we executed last time. Let me copy. Good. And let me paste into the console. Right mouse, paste. Now I'm getting a warning. The warning says it's unsafe what you are doing. Let's forget about it. Okay, and here we see a first example of cut and paste, which allows us to repeat what we did last time, actually. Now, let's copy the last instruction that we executed last time. So I go back to the list of instructions. I am now copying the last instruction we executed last time. Copy. And I go again to the console. Here we are. Paste. Let's ignore the warning. Oh, yeah. Just 1 second. I forgot to put the file that I wanted to read in the right place. So let me just change it, and let me just doing very quickly. I go out and restart R from the correct location. Just 1 second. Give me 2 seconds. Yeah, it is in desktop. Okay, good. Okay, now I'm back to R. And let me do again the cut and paste. Up to the last instruction we executed last time. Copy. Now I can go here, paste. Good. This is where we got last time. What did we do in the last instruction? In the last instruction, I read the file that gives the coastline geometry. Where did I take this file from? It is in my website, actually. Let me go to it. It's here. You see that there is a file reporting the geometry of the shoreline. It is precisely this file that I'm pointing with the mouse now. I downloaded it with, for instance, the right button of the mouse, save link as. I downloaded it, I put it in a directory, in the same directory from which I am running R, and then I could read it with R. Just let me have a look at this file. Instead of downloading, let's see it. It is a file that gives 20 couples of X, Y, or it's a file that gives 20 coordinates of the coastline. In the first column, you see the coordinates of the coastline, and in the second column, you see the coordinates of the limit coastline. Just 1 second, because I want to make sure that you can, yeah, you can still read me. Okay, so again, this 2 columns are 2 columns of coordinates of the coastline and limiting position of the coastline. So what is the spatial step? Again, it's a spatial step of 150 meters. Okay, that's fine. Where can I read the spatial step? It is given in the second file, the file of wave forcing. You see that there is the first row that gives 150. This is actually the spatial step of the coastline. So we basically told the surveyor to take a survey of the coastline with a spatial step of 150 meters, and the surveyor gives us the coordinate of the position of the coastline. Okay, good. Not only the position, as we saw, but also the limiting position. The limits is something that for some reason cannot be trespassed. It can be useful. We will not use this second column of data. We will not impose any limitation to erosion. But in some cases, there are limitations, like if you build a seawall, there is a limit that you cannot pass. Even if you have erosion, when the beach gets against the seawall, then this limit cannot be passed. The seawall cannot be eroded, provided it doesn't fall down. Okay, good. Now, this information, both the coordinates of the coastline and the information contained in this file that you see on the screen, whose content is described in the text of the exercise, this information needs to be uploaded into R. And we did it by saving these files in the R directory and then reading the file with this instruction that you see here. It's a scan instruction, and I executed it already. Let me execute it once again. Let's see what is contained here in this vector PR1. First of all, this is a vector which reports, you see, in the first value, 426, you can recognize the first coordinate of the shoreline. The second value is the corresponding limit position. So basically, the two columns were placed in only one vector, and we cannot recognize each column here. Numbers were placed in only one vector. So in order to see again the two columns, and I go back to the website, and give me 1 second. I go to the file of the geometry of the shoreline. In order to see back these two columns that you can see now on the screen into R, I need to transform this vector into a matrix. Okay, let's see if I have the instruction in my program. And you see here, there is a following instruction, which I am selecting now, that now I am copying and pasting into the console. And let's see what happens. And I am commenting after I pasted on the console. So here, what you see is that the same variable, which I called in the previous instruction PR1, it's transformed, is reassigned. And so I can see that the instruction is PR1 is equal to an array, so a matrix. It's a function, and the argument is to be given between parentheses. Then it's a function, and the array is to be built by using the previous vector PR1, and the dimension of the array is 220. Now, if I press return, the instruction is executed and the array is built. You see, I created an array, and you see the dimensions now. I can see first the first column and the second column with the index 2. If I want to see only the first column, I just have to write PR1 1, comma, between parentheses. This is the first column. Second column, PR1 2, comma. Now, the first column is the position of the shoreline, and the second column is the limiting position. So what did we do with this series of instructions? I uploaded a file into R, a data file, in the form of a vector. The vector was obtained by scanning the data file. And then I transformed the vector into a matrix. It is more convenient because I can recognize much better each column of data. I hope this is clear. I understand that, you know, it's not straightforward. I tell you, when learning to use R, importing data, I think, is one of the most delicate steps. So once that you learn this step, the remaining part of the exercise is straightforward. So on the one hand, if you could follow me and you have in front of you an R console open with already the vector uploaded, the matrix uploaded, then that's perfect. In case you are a bit delayed and you can't follow for some reason, I just would like to tell you, don't get discouraged, because I'm sure that if you try, you get to this point. Do you have any question related to this? Any doubt, any problem that you want to discuss with me? Okay, I see. It seems that you don't have any question, any doubt. Let me continue then. Now, there is a series of further scan instructions. You see, first, there is an instruction that is scanning the spatial step. I'm calling it dy from the file waveforcing.txt. It is the file of, it is the other file. Let me bring the instruction into the console. So you see that the instruction is a bit different. The scan instruction is a bit different with respect to what I uploaded before. There is the name of the file, like there was before, but now there is the specification that I want to upload just one number. Let's have a look at the file again. Sorry, I am dedicated some time to these steps because I know that they are not so straightforward. I'm opening the file of the waveforcing, and you see that the first number in the top is 150. And this is precisely what I gave the instruction to take. I said, read one number only, and this is the first one. So let me go back to the R console. Let me see if the Y is indeed equal to 150. Yes, it's there. Very good. So let's move forward. Next instruction, and let's take just one for now. Copy. I am commenting once I pasted. I am commenting here. So it's again a scan instruction, same file, waveforcing, but now I'm adding something, another argument, which is skip. I'm telling the instruction to skip one number. Why I am skipping that number? Because it's already uploaded. And then I am specifying to read one subsequent number. After skipping the first one, I'm reading one more. So I'm reading the second. Let's see what is the T. It's 120 seconds. Perfect. Very good. Now let's move forward with the other instructions. Number of time step. You see that here skip is equal to 2 because now I need to skip two numbers. And the reason is that these two numbers were already uploaded. And then I am uploading the wave forcing. This wave forcing is given by a matrix. So I need to transform the uploaded data into a matrix. And this is why I am also selecting the instruction array. Now, sorry, I deselected my instructions. Now I am copying, go to R, pasting. Here we are. And if you look at the last matrix we uploaded, again, we have the matrix that is interesting to us. Very good. So I think we uploaded all the data that we need. Very good. Let me clear the console now. And let me go back to the list of instructions. Now, in order to have the data more, let's say, ready to be used, I extract this data from the matrix and I assign them to vectors, meaning that I am extracting each column of the matrices that I uploaded, two matrices. I am extracting their columns and allocating these columns into vectors. So the first vector is called XLC, and you see it here, is the first column of the geometry matrix. In fact, you see the comment position of the cost line, which means that I am assigning to the vector XLC the position of the cost line. The position of the limit cost line is assigned to the vector XLCL. Very good. There is a test instruction that we are skipping, and then I am now extracting columns from the wave forcing matrix. The first column is the position of the breaker line. The second column is the wave height at the breaker line. The third column is the wavelength at the breaker line. The fourth column is the sea bottom depth at the breaker line. And finally, the last column is the wave angle. The wave angle. We will see in a moment later what angle I am referring to. We are referring to. Very good. Now let's copy these. And let's paste them into the console. Paste. Let's ignore the warning. Very good. So now let's make some test. XLC, this is the position of the cost line. XLCL, this is the position of the limiting cost line. You can recognize the numbers. So uploading was successful. Now position of the breaker line. Good. And length, wavelength at the breaker line, LF. Very good. dB, sea bottom depth, alpha. It's in radiant, I guess. Yes, it's in radiant, the wave angle. Okay, now let's clear the console. Good. And let me go to the next instruction. The next instruction is taking a cumulative sum of the dy's. It is meant to construct a vector of y coordinates. I am summing the dy's, the delta y's. I am summing 150 plus 150 plus 150, etc. Let me paste it in order to get a vector of y coordinates. So what is y here? You see, it's 150, 300, 450. I just take the cumulative sum of this vector of coordinates. It's not starting from 0, it's arbitrary. It's starting from 150. It's just arbitrary. Okay. Now let me go back. And now it is. Now we are creating a copy of the position of the cost line, just to keep it into the memory. Just 1 second, because I want to copy also the next instructions. The next instruction is a plot instruction. So it's an instruction that we still don't know. Let me paste it and let's see what happens. So I am copying and pasting here in the console. Paste. Now let me move this window, which appeared here. And let's have a look at the instructions first. Okay, there is the instruction to keep into memory the original position of the coastline, of the shoreline. It's I am creating a variable XLC old, which is just precisely equal to XLC. Good. And now there is the plot instruction. Let me just have a look at it. It's plot X, Y, type equal L. First, look at the round parentheses. So the plot is a function. For arguments of the function plot, I precisely gave the X coordinate, the Y coordinate, and there is also an argument type, which means line. Let's have a look at the result now. Forget about the red line. Let's have a look at the black line. It is a plot of the position of the shoreline. Here you see that if you look at the axis, the labels of the axis, you have Y on the vertical axis and XLC old on the horizontal axis. What I just typed is, with the black line, the sequence of the coordinates of the position of the coastline. Just to be clear, the sea is on the right. The sea is below the black line. What is the red line? Look at the console. There is a further instruction, lines. Lines is an instruction to draw a line over an existing plot. And of course, I need to give the coordinates of the line, and the coordinates are, you see, XLCL, which is the limiting position of the coastline, and again, Y. Let me just look at the plot. The plot is a bit, let's say, it's a bit misplaced because you see that the red line goes out from the plot, which means that probably I should have set the limits of the axis in a different way. And let me just now change these limits of the axis in order to include the full extension of the red line. Let me change the plot instruction. And what I need to do is to give two additional arguments. These additional arguments are Y limits equal to a vector 0. And the upper limit is, let me have a look at the plot. I can give 3000. Good. And now let me give also a argument X limit. And what kind of limits can I give? Let's say, I think 300, and the second one is I think 1400. Let's see how the plot became. Okay, I think it is nicer. And let me repeat the instruction lines. Okay, I think it is definitely nicer. We are now including the full extension of the red line into the plot. In the file that you will download on my website, there is already the modified instruction with the limits of the axis. Okay, good. This allows us to get an understanding, a better understanding of what we have to do. And in particular, let me just discuss with you a little bit the plot that you see on the screen. But let me, in order to be able to modify it, I want to copy it. And let me see if I can make a copy. If I click on the right, it should, just 1 second, should allow me to copy. For some reason, let me see if I can. For some reason, it doesn't allow me to copy. So I can make a different thing, because I wanted to put it into graphic blackboard, but I don't know why it doesn't copy. Let me just 1 second. I try to expand it. No. Even if I expand, there is no way. Okay, so let me just do another thing. I take a screenshot. Okay. Good. Copy to clipboard. Very good. And now let me put it into the graphic blackboard. Edit, paste as layer, new layer. Okay, here is my figure that you can see on the screen. Now, here we have some points. Let me just see if I can write something on the blackboard. Yes. Very good. Okay, here we have some points. So this is the first point of the coastline here. And then here there is the second point. And here there are the other points. Now, and here I have my steps. This is delta y. And I think there is another point here. Yes, and then there is another delta y here. There is a sequence of spatial steps. For each one of these, I need to compute the along-shore sediment transport. And then I need to check delta y is here and here. Okay, so each time step is a delta y. As I said, for each spatial step, for each of these steps, I need to compute the sediment transport. And then I need to compute the difference, because at each spatial step, let me depict, let me make a larger figure here. Let's suppose that I have these two spatial steps. What I need to compute is the sediment transport in this, so let's call it QL here, and QL here. And for each of these steps, I have to make a balance between, a difference between what is eroded in the previous time step and what is eroded here. And if I see that in this time step there is more erosion, and the direction of the longshore sediment transport is this one. If I see that here in the first spatial step I have more erosion than in the second spatial step, it means that here I have the shoreline that sets back, but then what is eroded here is brought into the next one. So if in the next one I have a smaller erosion, then I have the accretion of the shoreline. And then, of course, I have to connect the erosion in the first spatial step with the accretion in the second spatial step. And of course, this connection cannot be done with a sudden change. I cannot connect in this way. Okay, so I cannot say that the new shoreline is this one. Given that I am computing what happens, I am computing the evolution of the beach by spatial steps, of course, I have a numerical approximation. So the change is concentrated at the transition between the two spatial steps. What I need to do at the end of the story is to smooth this changes, this step changes. So what is going to happen is something like, let me see if I can change the color. Just 1 second. Let me just, okay. I cannot change the color now. Give me just the license to draw over here. What I have to do is to smooth the changes. So once I computed the changes by each spatial step, I need to smooth the resulting line to make it more regular. And this computation is to be done for each spatial step on this graph. Okay, now let's look at the program by keeping in mind always the presence of this numerical approximation. So we are concentrating the changes at the transition between steps, but actually this is an approximation which needs to be resolved, as I said, by some smoothing of the results at the end of the story. Okay, let's now go back to our instructions. What I need to compute, as I said, is the along-shore sediment transport, and therefore, let's call it QL. QL is the sediment that is transported in each spatial step, in each piece of the beach. I have 20 pieces, 20 spatial steps, so I am expecting to compute a vector of QLs, a vector which has a dimension 20. So I am defining this vector. At the beginning, I am defining the vector QL as a sequence of zeros. You see, repetition of zeros by 20 times. So let me define this vector. Copy. Very good. Let me go back to the R console. Just 1 second. Here it is. Paste. Now, if I look at the vector QL, I have the sequence of zeros, which is perfect. Very good. Now, let me move forward. And now I am making a computation that is to be repeated for each spatial step. And therefore, I am doing a cycle of computations. Cycling and conditions are the basic structures for any programming language. How to write a cycle in a given programming language is the first thing that you need to learn in order to be able to make a program. How to make a cycle, how to make a condition. Today we are not talking about conditions, but we are introducing cycles. A condition is an if instruction, like if a certain result is lower than 0, then make something. We are now today forgetting about conditions, about if instructions, but let me concentrate on the cycle that we strictly need because we have to repeat our computation several times. So how to write a cycle? A cycle in R is written with the 4 instruction. Let me copy it. And let me paste it into the console. So you see that I wrote for j varying between 1 and 19. So j is a cycle variable that is updated each time a cycle is completed. So if you start, if you want to repeat a cycle 19 times, then you have to set a variable which I called j here to be, as I said, updated each time you complete the cycle. Okay, now let me go back and let's see what is the cycle that I am, what is the instruction that I am repeating 19 times. Let me first paste it. Paste. Now, what did I do here? First of all, the cycle, if it contains only an instruction, then it doesn't need to be included into the curly brackets. So let me repeat the cycle. This is the cycle, the first instruction. If you look at what I wrote before, there was a curly bracket, opened curly bracket. I opened a curly bracket, and then I put the instruction to be executed into the cycle, this one. And then I closed the curly bracket, and the cycle was executed. Let me make another example, which is easier. Let me clear the console. Now, let me open the curly bracket, and in order to, it depends on your keyboard. In order to get a curly bracket on my keyboard, I press on the key Alt-GR, which is on the right of the space bar. I keep it pressed, and by keeping it down, I press on the number 6. Oops, sorry, number 7 then. Let's see, number 7. This is the curly bracket, and now let's give the instruction to be executed in a more clear way. Let me tell him to write on the screen, this is a cycle. And let me put a full stop here. This is an instruction, what I'm writing, that tells R to write on the screen. Now I close the curly bracket with Alt-GR plus 0, and you see that it was written, this is a cycle, 19 times. Very good. Now let me repeat it, another example. I'm going to the previous instructions with arrow up for J in 119. Let me skip the brackets. And let me just put the instruction. See what happens. Very good. It is the same result. So you see, when inside the cycle I have just one instruction, I don't need the curly brackets. The curly brackets are needed when you have more than one instruction. And let me give another example then. For J in 119, curly bracket. Now let me write the previous instruction, and let me write again. This is the second instruction. Good. And now closing bracket, and you see that both the instructions were executed. I had two. I needed the curly brackets. I hope this is clear. Let me go back to our program then. Here, I could have skipped the curly brackets, but I just put them for the sake of clarity. Let me just now repeat, cut and paste everything I did. I am repeating everything I did because I need to do it, because I executed the cycle twice, which means that I made a computation 2 times while I need to make it only once. So let me, sorry, just 1 second. The dog is a bit noisy. So I am pasting it. Very good. Here we are. Okay, so let's look at the last instruction I executed. What did I do here? Look, first, the instruction was repeated 19 times, and what I did is to smooth the cost line. I substituted each cost line point with the average of 2 subsequent points. This is a way to smooth a line, okay? And basically, why did I smooth it? Because when you get a survey of the cost line from the surveyor, then, you know, there is, as I said, an approximation, because it is a sequence of points. In order to make this approximation more realistic, in order to smooth the approximation due to the fact that I am collecting the shape by a sequence of discrete points, in order to mitigate this approximation, one possible way is to compute what is called a moving average. And this is precisely what I did with the 4 cycle that you can see in the bottom of the screen. I substituted each point with the average of 2 subsequent ones. And this average is moving. So this is an operation of moving average. Why did I do it only 19 times and not 20 times? Because, of course, given that I am substituting each point with the average of 2 consecutive points, in the last point, I cannot compute the average. So the last point is kept as is because I don't have the subsequent point. So I cannot compute the average when I am at the last one. So let me just make a sketch in order to clarify what I am doing. So here I have, just one second. Here I have a point on the coastline. It's not driving. So let me take another blank, perfect. Here I have a point on the coastline. Here I have another point. Here I have another point. So what I'm doing is to change this point. I bring it here because it's the average between this one and this one. Now I am substituting this point. I bring it here because it's the average between this one and this one. For the last one, I don't have the subsequent one. I don't have it. And therefore, I leave it where it is. So instead of having a line that is connecting in this way, I have a line that is doing this. Again, I smoothed the coastline. Perfect. Now let's go to, again, to the next instructions. I bring the file up. And now, let me select. I have another 4th cycle, but be careful, this 4th cycle is computed along time. A long time because you see that the variable, the cycle variable, which is called I, varies between 1 and the other extreme is the number of time steps, n delta t. And you see the comment, cycle along the time steps. Okay, very good. Of course, you can increase n delta t. If you want to continue your simulation for a longer time, you can continue. Very good. Now, given that I have many instructions inside this cycle, let me open a curly bracket. Very good. Now, what I am doing here, sorry. Just one second. What I am doing here, just one second, because I deleted the lines that I wanted to execute. So edit. Just okay, give me 1 second. I am reopening it. Okay, here we are. Very good. Now, as I said, we open this cycle with the bracket. What do we have later? Another cycle. This is fine. Cycles can be nested inside each other. And the next cycle is along the spatial steps. So it's a cycle along the shoreline. So at each time step, we make a computation of the sediment transport in each spatial step of the beach. Very good. Let me open another curly bracket. And then let me explain what I am doing here. Basically, I am starting the computation of the sediment transport in each time step. In order to do that, I need to compute the acute angle, as you may remember, between the wave direction and the direction of the coastline. Now, in order to explain what I am doing, let me refer to the text of the exercise, which is somewhere here. Okay, let me go in the second page. Now, you can see here I have my coastline and I have the wave approaching. Look at the black arrow. Very good. Now, the angle that I am given in the file is alpha. It is specified in the file. This is the angle between the wave direction and the y-axis. So in the file I have this angle. What I need to compute is, look at the blue angle, alpha 2. This is what I need, the acute angle between the wave direction and the coastline. So how can I compute this? Depending on alpha. First of all, I need to quantify the direction of the coastline. I need to specify it. So I need to compute the angle alpha 1. Look at my mouse. This angle between the vertical axis and the coastline, alpha 1, gives to me the direction of the coastline. So in order to compute it, what I have to do, I have to compute the ratio. This is a triangle, rectangle triangle. I have to compute the ratio between the x and the y and compute the inverse tangent, and I get alpha 1. If you remember trigonometric calculation, with the trigonometric calculation, one can say that dx is equal to dy times the tangent alpha 1. So in order to compute alpha 1, I have to compute the inverse tangent of the x divided by the y. Perfect. Once that we have alpha 1, well, alpha 1 is repeated here, and you see that alpha 2 is equal to alpha minus alpha 1. So this is what I have to do for each spatial step of the beach and each time step. Before doing that, let me just make another smoothing, because the direction of the coastline is changing at each spatial step, and this change in reality is not very sudden. It's smooth, of course, because the coastline is modeled by the waves. It's a continuous process. It's not a discrete process. While in my survey, in my discretization numerical approximation, I have steps. So I need a second smoothing. Of course, this is not strictly needed. It's just something that in this case, I believed it was appropriate. So after smoothing the coastline with the moving average, I want to compute another smoothing. So let me now go to the program and see what we did here. You see that the second fourth cycle starts from 2, not from 1, and goes up to 19. And let's look at here. I am computing an auxiliary XLC value, which is given by the difference between XLC II plus 1 minus XLC II minus 1, which means that I am basically computing the coastline direction across 3 points. Let me explain better here. And let me make another sketch. So what I'm doing, I have a coastline with, let's say, 3 points. Okay, this is my actual, or the coastline surveyed by the surveyor. And here I have the spatial step delta y and delta y. Very good. Now I could compute if the wave here arrives in this step along this direction. I could compute this angle here, and I could repeat the same angle here. Let's suppose that the wave has the same direction. Actually, it is changing. In each spatial step, it's changing. But let's suppose here that it has the same direction. I can compute two different angles in these two delta y. What I'm actually doing in reality in my exercise is to connect these 2 points, to connect these 2 points. Good. I am computing here a delta XLC, which is my XLC aux. And then I am computing this angle here. So basically, I compute the angle of the wave here and here by connecting 3 points, not just 2. And again, this is another way of smoothing. This is something that is just motivated by a numerical consideration. So it's not really something that it's strictly needed. It's just basing on the sensitivity of the programmer. Okay, good. So you see that here there is the computation of the auxiliary XLC, and then here I have the computation of the angle. You recognize the inverse tangent here. And then here I have the computation of the average wave height, because this is a wave forcing data. I am computing an average over the 2 steps, 2 spatial steps. And then here I am computing the energy of the wave, the energy per unit vertical transversal area, and finally QL here. Good. Let me execute this one. Let me just see. Okay. Let's just make this cycle. Copy. Paste. It's not completed because look at the sequence of the curly brackets. I open 2 and I close only 1 because there are still instructions in the first cycle, which is the time cycle. So let's paste them. I go back to our file, and then I am computing here the differences between the QL in each spatial step. The function diff computes the difference of a vector, differences of numbers inside a vector. Very good. And then if you move forward, you see another cycle where I have the computation of the shift of the shoreline. The Xi is the movement back and forth of the shoreline. And then I have finally the computation of the new position of the shoreline, the new XLC, which is given by the previous XLC plus the Xi. Let me compute this. Okay. Copy. And then paste. It should work. Okay. Everything was done. Was repeated for each spatial step and each time step. Good. Let me clear the console. What I just need now is to have a look at the new shoreline. Let me print it. Okay, let's have a look at the graphic window. You see what happened. The blue line is the new coastline. But let me have a look at this instruction, the last one that I just put over the screen, and then we will make a recap, a summary of what we did. If you look at the last instruction, it is plotting the new XLC with the lines instruction. So this is XLC, sorry, I go to here, I go here. This is XLC, and this is the lines instruction. But there is in between an additional function that we still don't know, which is called lowes. What is lowes? Lowes is a smoothing function. It's a function that makes the same effect with respect to a moving average. I could use a moving average here. What I wanted to do is to smooth the new coastline, again, in order to transform the numerical result into a more realistic result, in order not to concentrate changes in specific points. So the question may be, why didn't you make a moving average? Just for teaching to you, just for informing you about an alternative method. This smoothing function has parameters, and in particular, it's the parameter, the smoothing parameter is f. If you increase f, you increase the smoothing. Let me have a look at the graph. Still, you see that the new coastline is a bit steppy, and it's still a bit steppy. So one may say, why don't I smooth maybe some more? Let's make an experiment. Let's make here f 0.6 and see what happens. You see, I got another blue line, which is more smoothed. And probably it would be better if I put this in not in blue, but let me put it in like, I'm not sure whether it takes purple. I think so. And let me also make it thicker, so it is more easily readable. You see, if you look at the purple line, you see that it's indeed a smoothing of the blue line, and it's more realistic. So you are basically, let's say, distributing along the shoreline the changes that have been modeled, detected. Now, the question may be at this stage, what if I make the simulation longer in time? Well, this is very easy. If you go back to the program, now that the program is done, you can basically say, let me see, I don't remember what is the value of n delta t. It's 1000. Let's make it 3000. So you go back to the program, and here, instead of scanning the value of n delta t, here you put 3000. Let's see if it works. What I just have to do is to select everything. I select the whole file. Let me copy it. I go to the console, and to the console, I just paste. Paste. Let's see the result then. So you see the result here, and you see what happens if you increase the length of the simulation. So first of all, you get with the blue line against the red line, and we didn't put any control here in order to make sure that this doesn't happen. So this is something that we should adjust, because if there is a limiting position of the coastline, indeed, we have to make a condition in the program. to say that if the blue line passes the red line, then make the blue line overlapping the red line. But we said that we don't consider today conditions. So let's forget about it, okay? The second issue is that you see, by expanding the simulation, what we get is a more steppy new coastline. So it's something that we have to change by increasing the smoothing. If you look at the instruction on the left, we kept a f parameter equal to 0.38. Let's try to increase it. So let's repeat everything. Let me go back here. The difference is that I have to change in this file f 0.38. Let's use f 0.6. And then let's repeat everything. Copy. And let me paste it. Very good. Let's see the result. Now it's more realistic. You see, the blue line is more realistic. And you have an idea of the progress of the coastline. There is one thing that I wanted to tell you, actually. You may you notice that at the beginning of the beach, on the left of the graph, you have indeed the blue line approaching the red line. Do you know why this happened? It happens because actually I didn't put any boundary condition in this computation, which means that the value of QL is set to 0 in the first step, which means that at the beginning, in the left of this diagram, given that you have QL 0, which means that no sediments are entering into this piece of beach, you have a strong erosion. If I put a boundary condition like a QL different from 0 at the beginning, then I wouldn't have this effect. This is something that you can experiment by changing the program. Actually, it is not straightforward, but let me see the values of Qn that we have. You see, let me again. You see the values of QL? Basically, you have 0 at the beginning and 0 at the end because we didn't put any boundary condition. If you change these values, and I think it should be a negative value, meaning, anyway, we can try. Let me put as QL1 equal to QL2, QL1 equal to QL2. And this is a way of giving a boundary condition because I am equating the first two numbers. Now, if I display again what I find, you see that I have the first two values that are equivalent. And then what I need to do is to repeat the computation. So let me just go back to the program, and here what I have to do is to put QL1 equal QL2 here, so that the instruction is repeated each time. So let's see what happens. I again copy it, copy, and paste it here. Paste. Very good. Let's see. You see that something changed a little bit because the blue line indeed came a little bit more offshore. And of course, I could make a different boundary condition. Let me make another experiment in order to shift it more because the effect is not very visible. So let me have a look at the values of QL because let's try to put equal -1. I think this is exaggerated, but let's see. Copy. This is exaggerated a little bit, probably. Paste. Let's see if I don't have mistakes. When you change programs, if you put unrealistic values, you may get errors in the computation. It seems that I didn't get any error, but let me see what happens. No, actually, I obtained the opposite result. So let me change again. And instead of -1, let's put +1. This is actually what intuition suggested to me, but let me check. Paste. Didn't change much. Actually, what changed is at the end, probably because, okay, probably because we need to articulate the changes in, we need more attempts in order to try to better understand what's going on. Let me see, just, let me say one last thing, by the way. When you make these attempts, every time you have to cut and paste, which is something that is a little bit boring. So how to avoid this? There is a very simple manner. If you look at your file, this is a file that is placed in the R directory. And there is an alternative way of cutting and pasting a file into the console. The alternative way is if you use the instruction source. And you need to put the file name between commas. And let me see, in order to find the file, it's just enough that you type the first 2 letters and then you press the tab button. And you see, everything has been executed and repeated here. Now let's make this other attempt. Now, if I want to make other attempts, like repeating the file in the original form, so removing this boundary condition, I just have to save the file, of course, go to the console, and again, source it. Let's see what happens. So indeed, you see that the boundary condition is that I gave is not very effective at the beginning of the simulation. It becomes more effective at the end of the simulation, probably because it is shifting the shape of the whole coastline. And so if you want to place the boundary condition in a resonant manner, we need to make additional considerations on what can be the reasonable value for these boundary conditions. If we put values that are just drawn by chance, what you may obtain is something not realistic and something that is indeed producing an effect that is not really what we wanted to induce. So I hope that this overview gave to you like an incentive to make additional experiments and to deepen your knowledge of R. Basically, what we did is, what we learned is how to write a program, because what we did is actually a program. It's a sequence of instructions. It's a program that is very useful when you need to repeat computations several times. For instance, like we did for finding ideal values of boundary conditions to be given, or for making several computations with respect to changing wave forcing. So what we did is a program that can be easily repeated for different conditions, different numerical strategies. And in order to run it, we just have to upload with the function source in the R console the sequence of instructions that we wrote. We learned how to write cycles. We learned how to nest cycles in order to perform simulations in space and time. And of course, we learned how to apply the CERC formula. Related to this last, I am sure that you still have some doubts, because when you repeat a computation that actually it is a bit complex, and you repeat it in 1 hour, and you repeat it by cutting and pasting from something that has already been done by others, it's not easy to get the sense, the essence of what you're doing in a first instance. If you were successful, if you didn't have any doubt, I would be very surprised. So it means that, of course, if you are interested, you need to try to understand in more detail what we did. And keep in mind that with the numerical approximation, there are some subjective, as we discussed, strategies that you may adopt. For instance, I performed several smoothing of the data. And I tell you, I needed to do that because I used for the wave forcing a real file, a real wave forcing file that I downloaded from a monitoring service in the United States. And when you use real data and you combine them with real data of a beach, you may run in a numerical approximation that is too rough. It's too much coarse. And this is what I experienced. Without the smoothing that I did, the numerical approximation would end up with a shape of the beach that is not realistic. And so this is why I introduced the first smoothing, and then I look at the result and I was still not happy. So a second smoothing, and then a third one. And in this further experiment that we did by extending the number of time steps, you see that I ended up with a shape that again was not satisfactory, is not very realistic. And so this is why I basically decided to increase the smoothing parameter. A final consideration. When I changed the boundary condition, what is the reason why I didn't get the desired effect? Basically, I put a lot of material entering into the beach, a lot of sand. But given that there is a quite significant eroding power, this material was transported at the end of the beach, because at the end of the beach, the second boundary condition was again 0. So all the material was transported. And this is why when I tried to put more material entering from the left, I found all the material in the right. So these are, of course, simulations that you may repeat several times and find the ideal solution that gives you a reasonable shape of the beach. A reasonable shape, what does it mean? It means that it corresponds to your intuition. So once again, it is very important to develop a preliminary intuition of what the shape of the beach could be after a certain wave forcing. This gives you the opportunity to check your results and to adapt your modeling with your perception of the reality, because keep in mind that any modeling is an approximation. It's an approximation that needs to be matched with a perception of the reality, needs to be matched with the reality that you see, and if you don't see it, the reality that you can perceive. Now, with the awareness that this hour may have been a bit tiring to follow, I wonder if you have any question now. Let me look at the chat. I don't think, no, nothing there. And let me see how many you are. 5. Okay, now, if you agree, what we could do now is to start the survey of your opinion, and then we move forward with the next lecture. So if you agree with this, what I would like to do is to tell you in 3 minutes what is the purpose of this survey. Maybe that you have already heard this discussion before, but actually I think that I may give you an interesting perspective, because I think my perspective is a bit unique. And also I am supposed to introduce to students the meaning of the survey. So this is something that I am asked to do by the university, and I'm very happy to do. And so I will introduce to you the survey, and then let's make 10 minutes break so I can prepare the survey, and then we make it. So why the survey? The survey is used by the university, and it's suggested by the Ministry of University in Italy, and it's actually compulsory. So the universities are required to take the opinion of the students, and there is subjectivity in order to how these opinions are collected, so how the questionnaire is shaped and how the results are used. The shape of the questionnaire has been changed this year in order to take into account that the way of teaching is radically changed, and we passed from, as you know, from physical presence to remote teaching. Actually, the way the results are used is not changed. The results are used by different bodies into the university for evaluating strategic moves in order to try to meet the demands and the ambitions of students. The results are used by the quality assurance service of the university to work with the professors, to stimulate the professors to improve the quality of teaching. And actually, the results are also used for allocating resources to professors and departments. So it means that, for instance, a professor for getting the regular increase of salary is required to meet certain thresholds in the students' assessment, students' opinions. These thresholds actually are not very strict, but still there is a motivations for professors in order to try to keep their teaching at the pace of time, I would say. Not sure whether this is to be innovative, I would say. It's an incentive to professors to be innovative in teaching. And also it is used for allocating resources to departments, resources that are human resources, financial resources to support the teaching activities, because the teaching activities are under the remits and responsibilities of departments in the Italian system. So, your opinion is really important. It really matters a lot, because, as I said, they help the university to allocate resources both to professors and departments and develop strategic moves. Besides, at a personal level, I would like to say that I'm very interested in your opinion, because for me it is something very important in order to shape my way of teaching and to identify the topics that are more relevant and more fitting students' expectations. In order to get the profit, to get the max profit for me, what I really appreciate is your feedback also in textual form. You know that the survey has a quantitative part, which is just scoring. So you put scores. And then there is a textual part where you are invited to motivate your assessment, your opinion, to justify your opinion. This is the part that is extremely important for me, because, the quantitative assessment doesn't say much. What I am really interested in is to get your motivation for a positive assessment or for a negative assessment. It doesn't matter. I would say that it's even more interesting. I would say it's more interesting, the motivation of a negative assessment with respect to the motivation for a positive assessment. And also, if you have any suggestion to give to the teacher, this is really much appreciated. Keep in mind that the questionnaire is anonymous, and therefore you don't have anything to be concerned of. And but really, it is something that I appreciate very much. A final thing. when you put your scores, you have four alternatives, which is something like definitely yes, yes, no, no, yes, definitely no. Keep in mind that the university, in making its quantitative assessment, groups the four alternatives in only two. So definitely yes and yes no are put together. Definitely no and no yes are put together. Just keep it in mind. First thing. Second thing, there is some statistical procedures to ensure robustness of the statistical assessment of your opinion, which means that extremes are neglected. So, I mean, you don't have to exaggerate in your judgment. If a judgment is extremely positive, it's overly positive, it's not helpful. If it is overly negative, it's not helpful. I mean, the judgment is helpful and effective when it's balanced. And this applies to several situations in your life, professional and personal life. So to be balanced makes your opinion more effective. And in whatever it means, I mean, if your opinion is not a positive opinion, if it's balanced, is more effective in changing the situation for the better. And so this is my personal suggestion. Try to be balanced, because to be unrealistic in both sides, it's something that doesn't help, and in particular doesn't help you to reach your target. Okay, so my suggestion is that we reconvene in 10 minutes, and then I give you the questionnaire to fill. Any question? Very good. So just give me, let's take 10 minutes, and I prepare everything. Thanks a lot. Okay, students, I put in the chat the link of the survey. You have to use your unique credential, and you have to use the code that is also put in the chat. Can you please, once that you finished, write on the chat something like "I am done," something like that. And if you need additional instructions by me, just let me know.